Hi, welcome to Sam's Maths Lectures. So I'm going to be doing a series of videos about path integration. So path integration is a sort of extension of integration from being over sort of a finite number of variables to being over an infinite number of variables. So you could possibly think of integration as being integration in one variable. You can think of as being something like area under a curve. So we have f of x, and the integral of f of x is going to tell us this area. This is the integral between 2 points. This is 0, we'll call this a for more generality, we'll call this b. Then the area is the integral from a to b, f of x dx. That's not a super rigorous definition, but it's the one I'm going to give. Path integrals are not at all mathematically rigorous, so we're not going to focus on rigor. Much more about sort of intuition and important results. Okay, and so then let's say we had instead a function fxy, so z equals fxy. This is going to be a sort of surface in xyz three-dimensional space, and we can think about the volume contained in a region. Let's try and draw this. So this is the z-axis. Which way do I want it to be? Yep, y coming down there, x here. So we've got some sort of surface here. Maybe I should have drawn this previously. Let's try and draw a surface in here. Sort of straight lines passing through it. Okay, brilliant. There we go. So we've got this curve. We've put that z is greater than 0 for this function, and then we can sort of mark out a sort of rectangle from a to b along the y-axis and c to d along the x-axis, and then what we do is we sort of track these points up, and we've basically got sort of mostly a cuboid, but then it's sort of bottomed out by the xy plane, but then on top of it is the surface of this curve, and the volume of this cuboid is the integral from a to b, integral from c to d, f of xy dx dy, and we can continue to higher and higher dimensions. So we can have 3 variables, 4 variables. Path integrals are sort of what happens when we take a continuum of variables. That's what we'll find, and so they're very important in physics. A very useful formulation of quantum mechanics focuses on a path integral as its propagator, its sort of function that determines evolution of systems. And quantum field theory, so relativistic quantum mechanics of particles, it's sort of one of the most complete and important theories in physics, is very much in the modern era built around path integrals. It also appears in other things. Statistical mechanics has path integrals. Things like random walks of a particle in space can be modeled using a path integral. Various things. So that's why I am going to be talking about it. Here I've put integral with the sort of integrand in the middle, with sort of our bounds here and our variables here. I'm a physicist, so sometimes I'll write things like a b dx f of x. You'll just have to get used to it, and this sort of the f of x you can think of as being in here. It's just a more convenient way of writing things, because then you can sort of think of it as just being a functional, we'll get onto what a functional is later, applied to the variable f. Okay, so to start path integration off, we're actually not going to do path integration. We're going to start by looking at Gaussians, because Gaussians are one of those things that you come back to time and time again in physics, and we're going to be using loads in path integration, because they're one of those things that we can do lots of things with, because they're particularly nice. It's a bit like the harmonic oscillator, and how we keep going back to the harmonic oscillator because it's something that we can always solve properly. And so we want to do as much as we can with it and turn other things into it as much as we can. So we're going to start with a Gaussian, or a bell curve, which looks something like this, except it's supposed to be symmetric. We'll put 0 here, or that's the y-axis, sorry. Here's the x-axis, it's y. Okay, so the Gaussian, you think of it as a normal distribution or a bell curve, and its f of x is e to the negative x squared. Obviously you can dress this up a bit. In statistics, you might see a probability distribution, which is some normalization factor that we'll work out in a bit. E to the negative, and then it's something like x minus the mean squared over a standard deviation squared. Maybe there's a 2 in here. We're not talking about probabilities this time. I'll make sure that I get the conventions better for next time. But for now, we're going to work out how to integrate this. So one of the problems with e to the negative x squared is that we can't find a indefinite integral for it. One exists, it's called the error function. So ERF of x is a function which is actually defined to be the integral from 0 to x, and then we'll say dy e to the negative y squared. What does this error function look like? Well, we can't write it out in terms of sort of elementary functions, so that's basically constant functions, polynomials in x, trigonometry, exponentials. Other things are called sort of special functions, and so f is a special function, and it's defined by this equation. Really, you can think of e to the x as being a special function. It's defined as the solution to dy dx equals y with the initial condition y of 0 equals 1. That's actually a full definition for what e to the x is, so it's also a special function, but we don't think of it as special because we use it every day. We know what e to the x looks like. We integrate it, we differentiate it, we like e to the x. The error function we don't like as much, we don't really use it at all beyond this, but it looks something like this. So let's make that flat. So this is error function of x, and we're going to work out what these values are in a bit, but it goes towards some constant with an asymptote here, has an asymptote here. It's constantly increasing because it's an integral of a positive function, so it's measuring the area under that curve. Well, if x is greater than 0, it's the area from here to x, which is obviously going to increase with x. And if x is less than 0, it's going to be the area from x up to 0, but negative, so again that's going to increase because the area is going to decrease. And the derivative is going to go off because the derivative is e to the negative x squared. Sort of fundamental theorem of calculus. So it's going to look something like this. It's got a sort of steepest point here. It has a gradient of 1, that's e to the negative 0. But we don't care about the error function because we're not going to be doing bounded integrals. We're going to be taking integral negative infinity to infinity e to the negative x squared dx, because this is something we can do. We can do this by a sort of trick where we say that, let's say a is equal to this, because we've decided it's some number. I'm not going to prove that this is bounded, but it is bounded. The limits do exist. You can safely take the lower and upper bounds to infinity without this thing diverging. Then a squared is integral from negative infinity to infinity e to the negative x squared dx times integral from negative infinity to infinity e to the negative y squared dy. That's fine. That's just writing the same thing out twice, because x is a dummy variable, so we're allowed to change it to a y in the second expression. Then we're going to do this thing called Fabini's theorem, which means that we can write this as, basically we can stick one integral inside the other one. When you can apply Fabini's theorem can be a bit complicated case by case, but here we can look at it and say, well, this is just a number, and so we can move it inside this integral. So we get negative infinity to infinity. My infinities are dreadful, I'm sorry. E to integral negative infinity to infinity e to the negative x squared dx e to the negative y squared dy, but then we can also swap these two around, because that dx integral sees e to the negative y squared as just a number, because we're performing that integral, we're performing the x integral first with y constant, so we can say this is e to the negative y squared dx dy. We're happy with that. Now this we can redo in polar coordinates, so this term here, e to the negative x squared minus y squared equals e to the negative r squared. Remember, in polar coordinates r squared is x squared plus y squared, and change of variables to polar coordinates, dx dy is r d theta dr. Okay, so I'm not going to go into this. I'm sure you already know, hopefully, otherwise look it up somewhere else. So this is the integral over r squared, so r times r, the whole plane of r d theta dr e to the negative r squared. This is why normally I put the integration variable first, because it means that I have more room to keep writing. Okay, so we can rewrite this integral, basically just elaborating on our bounds. So r is going from 0 to infinity, we're going from the origin all the way out. Theta is going from 0 to 2 pi. R e to the negative r squared d theta dr. Now the theta integral is integral of a constant, so we can just do that. That's going to be theta evaluated at 2 pi and 0, so that's going to be 2 pi integral 0 to infinity r e to the negative r squared dr. Now we can do this integral. We couldn't do the integral before, but this one is perfectly fine, because the derivative of this is nearly this. It's 2 pi. It's going to be negative 1/2 e to the negative r squared 0 to infinity. You can check that if you want. So differentiate this thing. We're going to get, that's going to stay the same, but we're going to pull out the derivative of negative r squared, which is negative 2r, times this by negative 2r, we get r. Good. That integral works. And then we just evaluate this at the bound, so that's 2 pi. At infinity, this is going to be 0, because this is going to vanish. Then this is going to be plus 1/2 at 0, because, well, it's minus a half, but then we're subtracting it, so we get plus a half, because this is going to be 1 pi. And so that means that the integral from negative infinity to infinity, e to the negative x squared dx is the square root of pi. Because we just square root, this is a squared, remember? So that's our first Gaussian done. Now we're going to start generalizing things, because we don't want this to stay, well, we want more integrals, right? We've done one integral. Turns out that's pretty much the hardest of the integrals we'll do for now. Everything else is just a simple change of variables away from being this. So let's start with e to the negative ax squared dx. And we'll say that a is greater than 0, because otherwise this won't converge, right? We want it to go like this. If a is positive, if a is negative, or yeah, if a is negative, then it's going to go like this, which is bad. We can't integrate that to infinity because that's going to diverge. And if a is 0, it's going to flatline. And again, we can't integrate that to infinity because it's going to be, the area under the line is going to be infinite. Okay, well, this one, nice and easy. We just say that let root a of x equal u, then change of variables dx is going to be du over root a. The bounds are going to stay the same because when x is infinity, u is still going to be infinity. So we get e to the negative u squared du 1 over root a. And so this is just root pi over a. So as a increases and we get a sort of sharper Gaussian, then the area is going to go down. So this is, let's say this is a equals 1, this is a equals 5, I don't know. So we shrink in our area. Next we're going to add a linear term, so not 1 over anything yet. Negative infinity to infinity, e to the minus ax squared plus bx dx. Now we don't care what b is. A still needs to be negative. B can be any number, because at infinity this term is going to dominate this term. So we still get our nice convergent properties. So b can be positive, it can be negative, it can be complex. Doesn't matter. So what we're going to say is that minus a x squared plus bx, that is minus a x squared plus bx over a minus bx over a. And we're just going to complete the square on that. So that's minus a, and this is x minus b over 2a squared, and then that's going to give us a minus b squared over 4a, sorry, plus b squared over 4a, so we need to subtract that back off, over 4a squared. X minus b over 2a squared times minus a plus b squared over 4a. Now what we do is we let u equal x minus b over 2a. Again, the bounds of the integral are not going to change, because when x is infinity, u is still infinity, because b is not bigger than infinity. And when x is minus infinity, u is minus infinity. So we e to the negative au squared e to the b squared over 4a du, because du is equal to dx. We can pull this out because it's just a constant, and so we get square root pi over a e to the b squared over 4a. Is that what I've got in my notes? That's what I've got in my notes. Brilliant. There we go. That's as general as we want to get in one variable. Obviously we could add plus c here, but then that's just going to give us an e to the c here because it's a constant, so we don't care about that. So what we're going to do now is we're going to expand this to multiple variables, n variables to be precise. So let's let x equal x1 xn. We're going to bring in this vector j1 up to jn. This is a real vector. Let me just check my notes. I don't think there's anything that prevents us from saying, nope, we can actually say that this is a complex vector and these are column vectors, so let's transpose them. There we go. And then M equals some block matrix. We're going to start with M11, M12, M21, dot dot dot, M, N, N. And this is, it's going to be a real n by n matrix. There's actually going to be some more conditions on M. We're actually going to require that M is symmetric. And it's going to be positive definite, which means that all eigenvalues are greater than 0. The reason for this is because, well, you'll see. Okay, and now what we're going to do is we're going to do the integral dnx over all of r to the n. So this is just dx1, dx2 up to dxn. Now we'll bring our differentials to the front in our integrals. E to the negative 1/2 x transpose m x plus j dot x. Why are we doing this? Well, it's the most general way that we can extend our single variable case. Obviously we could just do e to the minus ax1 squared minus a2x2 squared, blah 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 blah. That's boring, that's just going to be a product. This way we're slightly more exciting. We've got a general matrix in here. And we're going to examine this. So this is a sum from ij equals 1 to n of xi m ij xj. And so that's why it doesn't, we can say that m is symmetric, because we get that it's going to be the sum from I equals 1 to n, sum of j less than I, of xi m ij xj plus xj ji xi, and then plus sum over just the i's of, move this slightly, you can see it better, of m ii xi xi. So basically we've taken the terms and we've split them into 3 parts. We've got the I equals j has become just a simple sum here. This is where I is less than j, and then this we've taken j is greater than I, and we just flipped it round and sort of relabeled I and j. So we end up with this sum, and then that means that we only see these m terms in the form mij plus mji. So any anti-symmetric part of m is going to drop out of that sum, because then this term, it's going to be minus this term. It's going to vanish. So we can say that M is symmetric. Positive definiteness we'll get to in a second. Now, what's useful about symmetric matrices is that symmetric matrices are diagonalizable. What does that mean? It's sort of a theorem from linear algebra that any symmetric real matrix is diagonalizable, which means that we can find some matrix O, which is an orthogonal matrix. So this is matrices in R to the n times n, such that O transpose times O is the identity matrix, so an orthogonal matrix. And D, which is a diagonal matrix, so only elements on the diagonal, lambda 1, lambda n, such that, however written it, M is O transpose times D times O, and here lambda I are the eigenvalues of M. That should make sense. If you don't know what an eigenvalue is, this is probably not the video for you. Go watch some linear algebra first. Okay, so what can we say about this? Well, X transpose M X is going to be X transpose O transpose D O X, which is OX all transposed D OX. Then we have the J dotted with X. Well, we can write that as J transposed times by X, right? Because X is a column vector, J is a column vector, J transpose is a row vector. When we matrix multiply them, we're going to end up with a number. It's the dot product. So that's J transposed X. Then we can stick in an identity in here, but that identity could be O transpose O X. So we have this. That's OJ transposed OX. Now what we're going to do is we're going to change variables. We're going to say that Y is equal to OX. Now we're going to do some multivariable calculus and say that dny is equal to, and then it's the Jacobian dy dx of dnx. But this is very easy. This is the determinant of the modulus of the determinant of dy by dxj. But the y's and the j's are, y is a linear function of x, right? So yi is oij xj. There's a sum over j's in there, but I'm not including it because I'm a physicist. And so that means that dy by dxj is just o ij. That's a constant derivative everywhere, it doesn't change anywhere. So then this is mod of det of o. O is orthogonal, so its determinant is 1, or is plus or minus 1, so that's 1. And so what we get is our integral is equal to the integral over r to the n dny, and then we've got e to the negative 1/2 y transpose dy plus j primed dot y. and j primed here is this thing here. J primed. Now, what can we say here? What do we do next? Now, this is going to be integral. I'm going to drop the bounds of the integral there from 0 to infinity. So dy1, because let's do this properly first. Minus 1/2 y transpose dy is equal to, because d is diagonal, we find that dij is lambda I delta ij. So this thing selects out I equals j, and then it's 1. If I is not j, it's 0. And so we get minus 1/2 sum over j, sum over I, y j, lambda I, delta I, j, y I. Well, we can perform the sum over j, and this thing is just going to set j equal to I everywhere. That's minus 1/2 sum over I, yi, lambda I, yi squared. J primed dot y is just the sum over I of j primed I, yi, and am I going to expand this? Nope, I am not. I'm going to leave that as j primed I for now, and we're going to say that that means that e to the negative half y transpose dy plus j primed dot y is e to the sum over I minus 1/2 yi squared lambda I plus j primed I yi. That's good. That's looking more like what we had before, and so this is the product over all the i's, e to the negative half yi squared lambda I plus j primed I yi, which is good because we've split our integrand into a product of integrands, each depending on only one of the yi's. So now we can split up our integral as well. We got dny of product over the i's, e to the negative half y squared lambda I plus ji primed yi. Well, we can take that product and sort of swap it with the integral sign, so this is now the product of those n integrals. So integral dy I, just the first integral now, or the ith integral, e to the negative half yi squared lambda I plus ji primed yi. This is why we needed lambda I to be 0. Lambda I to be positive everywhere, because otherwise these integrals, some of them will diverge. So this is what we had before, and we've got that 4a is 2 lambda I, and b squared is j primed I squared, because a is minus 1/2. It's not minus, it's just 1/2 lambda I from our definition of a before, and b is j primed I for the ith integral. So then this is going to be the product over all the i's of square root 2 pi over lambda I e to the half j primed I squared over lambda I. And we can expand this product out. We just do the product, so the 2 pi, well, square root 2 pi times square root 2 pi times square root 2 pi, we just get 2 pi to the n. Then lambda 1 times lambda 2 times lambda n is the determinant of the matrix we started with. because the determinant of M is the determinant of D, which is a diagonal matrix, so its determinant is just the product of its entries. So this is det M, and then we get this exponential term, which is going to be sum over I of, take the half out, j primed I squared divided by lambda I. Well, that's the sum over I of j primed transpose d inverse j prime. Okay, because d inverse is going to be ij is just delta ij divided by lambda I. If you multiply these together, you see that we get two diagonal matrices, so we just multiply them component wise. Lambda I times 1 over lambda I is 1. So we can write this as times plus a half here. Then, well, that's 1/2 sum over I. Let's rewrite this as j O transpose d inverse OJ, and this is M inverse. And why is that? Well, O transpose D inverse O times O transpose D O. Those cancel, those cancel, those cancel. We get the identity. So this is going to be e to the 1/2. These shouldn't have had sums. That shouldn't have been a sum. That shouldn't have been a sum because the sums are in the vector notation. My bad. 1/2 j transpose, that's got a transpose on it, M inverse j. That is how we do a Gaussian integral in n variables, and this has taken me forever, so I'm going to stop and talk more next time about cumulant expansions. Thanks for watching.